My pleasure to introduce Jens Marklof from University of Bristol, who will tell us about the applications of measure rigidity from number theory to statistical mechanics. And this is the first talk in this series. The second talk will be tomorrow, Thursday at 4 p.m., and the last one will be on Friday, the 3rd.
Okay, thank you. And thank you very much for the invitation. It's really a great pleasure and honor to be here and visit. It's my first time at Stony Brook, and I'll be here till Friday. So if there's anything that comes up during my lectures, feel free to come and talk to me afterwards. I'm in office 5111, so you can find me there probably. Okay, so in these 3 lectures, I want to give you a flavor of measure rigidity, which is a phenomenon in ergodic theory that is very powerful and that has been able to solve a few outstanding problems in number theory and recently also in some other areas. One famous example is the proof of the Oppenheim conjecture by Marklof, and another famous example is Lyndon Strauss' work on quantum unique ergodicity, for which part of which he received the Fields Medal for. And these are all problems that people had tried using techniques from analytic number theory on harmonic analysis and failed. So what I want, I'm aware this is a broad audience, so all I want to achieve in these lectures is A, give you a flavor of what measure rigidity is. And measure rigidity in these lectures will refer to classification of measures that are invariant under homogeneous flows. So I'll have to explain to you what a homogeneous flow is. And then I'll go through a few famous examples in this lecture. The Oppenheim conjecture and Marklov's proof. Then some applications in quantum chaos. And I'll finish off with what I like a lot, some very simple sequences, number theoretic sequences on the circle that look random. And again, here you can use measure rigidity techniques to understand what the distributions are that you find there. And what is in particular fascinating in many of these problems is actually how easy and how simple they are to state and how hard they are to prove. Okay, and then I'll tell you a little bit about what I'm going to do tomorrow and on Friday. So the Lorentz gas is a very fundamental model in statistical mechanics that was designed by Lorentz over 100 years ago. And I'll show you there how measure rigidity techniques can allow you to solve an old problem. And I'll finish off with telling you a little bit about Frobenius numbers and circulant graphs. So let's start off. What's measure rigidity? And the way I want to explain this to you, I want to explain what measure rigidity is in probably one of the simplest dynamical systems, and that's just a rotation of the circle. So R modulo Z is just, that's how I think of the unit circle, or circle of length 1 is probably better. So let's take the unit interval and identify opposite points, opposite sides. And then you get a circle. And this equidistribution theorem is a beautiful theorem, and it's probably surprising to you that it was proved not 500 years ago, but just a little less than 100 years ago by Hermann Weyl, who is one of my great heroes. And what this says is that if you look at rotation, you iterate it n times, and you average some test function f. So f will be just a periodic function with period 1. You average it over the first n points, n tends to infinity. That will tend to the average of f with respect to Lebesgue measure on the circle, right? That's classical Weyl equidistribution. And I'm going to explain to you two proofs of this theorem. The first one is using harmonic analysis, which in this context means just using Fourier analysis. And then the second proof using measure rigidity. Okay, so that'll give you a flavor of what measure rigidity is. Now,
where's the rigidity? Where's the rigidity?
I'll show you. I'll show you. I've made a little, I mean, this is, of course, an old problem in distribution mod 1, and here's just a little numerical test where I've taken n to be 100, and then you count the number of n alphas that fall into a respective bin, and you get a picture like that. And of course, people have analyzed that pictures like this. So here's the first proof of measure rigidity, and that follows exactly Weil's paper from 1914, which is a beautiful paper. I recommend it to everybody. There's much more stuff in there than just this. So the idea is the following. We want to prove this statement, but it's actually enough to assume that f is a trigonometric polynomial, because these are dense in the space of all continuous functions, and then you can approximate every continuous function you want from above and below by a trigonometric polynomial. So let's just assume f is now of this form, a finite Fourier series. And so then we can commute these two sums, and we only have to, by linearity, prove the statement for each harmonic separately, right? So let's do this. Well, k equals 0 is a special case, and that's trivial. And then when we look at the non-zero Fourier coefficients, we're dealing with an exponential sum like this, which is simply a geometric sum. We can solve it. And what you see here, when you apply the classic formula, is that if alpha is irrational, that's the important assumption in this term here will be bounded, because this will be bounded away from 0, the numerator here, and the denominator, and everything else is bounded. So this is actually of order 1 over n, so this will go to 0. Okay? So that's done. That's the proof. That's Weil's original idea.
K is fixed.
And that's the important thing. K is fixed, exactly. And of course...
It didn't look true what you were saying.
Huh?
It didn't look true because the K is fixed, so it is true.
It is true, yeah. K is fixed. Capital K is fixed. All the K's are fixed. Of course, then when you start approximating things, you take K larger and larger. And of course, people then have, asked the question, what about when K is not fixed? Can you get exact estimates on the remainder, for instance, when f is a characteristic function of an interval? But I don't want to talk about that. But that's what I call the harmonic analysis approach, right? You expand into the harmonics, you estimate each harmonic separately, and you get your result. Now, what would measure rigidity do here? So now we will not expand things into the harmonics and try to estimate the error term. We'll argue simply by trying to understand what are the possible limits that we can get here. Limits of what? So first of all, look at this sum. This is the sum that we're interested in. In fact, we can associate a probability measure with this sum, right? Just by this linear functional. So in other words, we take the first n points on our unit circle, and we put a delta mass of equal weight on it, and we normalize it by 1 over n to make it a probability measure. So that's a probability measure, and now we can ask, well, we know that by the compactness of our circle, this sequence of probability measures is relatively compact, by which I mean that every subsequence contains a convergent subsequence. And so now let's just say, well, let's just assume we have a convergent subsequence with limit nu. What can nu be? Okay? Right. So in order to understand what nu can be, we have to understand the invariance properties of this nu. Now, this is the rotation that I've been talking about all the time. So x goes to x plus alpha. That's the continuous map of our unit circle. And let's look what happens if instead of f, I plug in the test function f composed with a unit circle. So I'm just rotating one more time. Then I'm looking at this sum. Let me use the pointer, then you can maybe see better. OK, so now I just write it as my original sum plus the extra term that I've got minus the term that I didn't have. So that's the same thing as up there. And so what you see here, because these guys go to 0, that the answer in the limit will be exactly the same as if I hadn't applied T alpha, my rotation, right? And the important observation is this is still a nice continuous function. So what you see here is that nu, my potential limiting measure, must be invariant under T alpha. So that's the one property we have. Number one. What else can we say? Well, if it's invariant under T alpha, it will also be invariant under any iterate of T alpha, right? And it will also be invariant under the closure of the group generated by the T alphas, right? And so now what are the measures that are, so first of all, what is the group that is the closure of these? Well, it's just the group of all translations. And which measure is invariant under the group of all translations? It's just Lebesgue measure. And you're done, OK? Because why? Now we know that for that particular limit point, we found its Lebesgue measure. But it's unique. We have got measure rigidity. So every limit of converging subsequence has to be the same. And that means that every subsequence will converge, hence the whole sequence, right? Because if you'd had a subsequence that wouldn't converge, you would find a convergent subsequence that would go to a different limit. But we know that there can't be a different limit. OK? Does that give you an idea what measure rigidity is about? It's about just looking at what the possible limits are, ruling out all the guys that you don't want. And if you're lucky, there's only one. You're not always that lucky. There might be a collection of possible limit points. But we talk of measure rigidity when the collection of possible limit measures is countable up to obvious isometries. And if you have such a situation, and you're lucky, and you can rule out all the other limits, then you know that everything converges to the thing that you want.
Did you say
calculable? Countable. Countable.
Okay.
So this is, and now here I've used 3 slides to explain to you the proof, the measure rigidity proof. Okay, so here it's clearly ridiculous to use this kind of argument. But now, in these lectures, I show you situations where the harmonic analysis proof simply doesn't work. And why? Because it's so hard to estimate the error term. In these problems, any estimate of the error term will be of the same size as the main term, and you're lost. Okay? While the measure rigidity technique, by completely making it unnecessary to talk about errors, just looking at the possible limit measures gives you the result you want. Good. So that's the first thing. The second thing is, as I mentioned, homogeneous flows will be the playing field here. And what is a homogeneous flow? A homogeneous flow is a flow on a homogeneous space. And by homogeneous space, in these lectures, I simply mean such a quotient space where you take a Lie group G, and then you take a lattice gamma in G, and you form this quotient. That's a homogeneous space, simply the collection of these cosets. And what is a lattice in G? You all know what a Euclidean lattice is, and these are generalizations to arbitrary Lie groups. So a lattice in G is a discrete subgroup so that there is a fundamental domain of the action of gamma in G with finite left Harm measure. Okay, so I don't know what all your background is, but the simplest example is, of course, take G to be, in my picture here, G is R2, and gamma is Z2. This is a fundamental cell of my action, and that's supposed to have finite measure with respect to Harm measure, which here is just the Lebesgue measure. Okay, and if you have this property, then you actually can show that the left Harm measure must equal the right Harm measure, so in fact your Lie group G will have to be unimodular. And now a homogeneous flow is simply the action of some one-parameter subgroup in G from the right on this space G mod gamma. So these are the things that we will use to study our problems. And the main example that we'll use, that will come up, and that also is the main example in most of the applications that are out there, is when G is the group SLNR, which is just the group of n by n matrices, real coefficients in determinant 1. And the discrete subgroup is the modular group. And Minkowski showed us that indeed the quotient G mod gamma has finite measure with respect to Harm measure. Minkowski computed this. Also, Siegel worked on this later and found beautiful formulas in this connection. And here are two examples of one-parameter subgroups that you can have. One is the diagonal group, and another one is this group, which I'll call unipotent later. And these are really the guys that we want. When n is equal to 2, there's a beautiful geometric interpretation of this flow. It'll just be the geodesic flow on the modular surface, because you can actually identify the unitangent bundle of the modular surface with G mod gamma. And this guy here, for n equal to 2, will be the horocycle flow. So for n equal to 2, these have a very beautiful geometric realization. Okay, so let's stay in let's keep n general, and let me explain to you why this quotient G mod gamma is interesting. Now, when I read, I should say this, when I read G mod gamma, okay, I really read it from right to left. Many people, it's a bit of a discussion of whether one should write it. And many people would like to, I even can't bring myself writing this, write it like this, okay? This is also fine. The two things are, of course, the same, right? You just transpose everything and you go from one to the other. In dynamical systems, people like writing it this way because they like the flow to act from the left. But I'm coming from sort of the automorphic forms, and there it's natural to write it the other way around, because, for instance, if you think of the complex upper half plane on which SL2R would act by Möbius transformation, that's a natural left action. So I prefer to write things from this way around, and it doesn't mean this is not the set minus, right? This doesn't mean gamma less than G. So I just point it out because sometimes people get confused about this. In fact, I just got a referee report asking me whether I couldn't change this thing around. And I will not do it if the referee is in the audience. It's too much of a change. And it's also a little bit of a point of view, I guess. Okay. Right, so the importance of this space comes in because actually it gives you a very natural generalization of what is called the space of lattices. And now I mean Euclidean lattices. So a Euclidean lattice in Rn of covolume 1. So covolume 1 simply means that the fundamental cell of this Euclidean lattice in Rn has volume 1. Every such lattice can be written in this way. You start with your cubic lattice, and then you apply a linear transformation. And because we want co-volume 1, this should be volume preserving. So that's exactly a matrix in SLNR. And so you can now find a bijection between a point in this coset space and the space of lattices of volume 1 by simply taking this map. And you can see that this map is well defined. To show that it's a bijection, you can easily find the inverse map. And you get this by simply taking a basis in your vector, in your lattice L. I think I'm not changing slides too fast enough for your machine. Are you used to more rapid talks? Or maybe this machine is. OK, so you just take a lattice in L, and you take a basis, so D basis vectors of your lattice L, because this is co-volume 1. If you write them as a matrix, so what I have to say here, I think of all vectors as row vectors. Okay, that's why I'm multiplying matrices from the right. So you make a matrix like this, and this will have determinant plus or minus 1, right? Because the co-volume is 1. And so I'm just going to apply some easy permutation matrix to make the determinant 1. So it'll be an SLNR, and that gives you exactly the inverse map. So I've just showed you that the space G mod gamma is actually nothing but the space of all Euclidean lattices in Rn with a fixed co-volume 1.
What do these two flows that you mentioned before correspond to?
Yeah.
Lattices.
Exactly. So the first flow, let me go back to the flow. That's just going to stretch your lattice, right? In different directions, and some contracting and others expanding. Because note here that the sum of these has to add up to 0. Otherwise, you wouldn't have determinant 1. So you stretch and you go. And we'll meet these guys later on. They'll both be prominent players in all our problems. And this one is just shearing it in a certain direction. So this is what's going on. And now let me show you how dynamics on the space of lattices was used by Margulis to prove this famous Oppenheim conjecture. So that was really the first application of homogeneous flow to a long-standing problem that many, many people had worked on, including Davenport and Heilbronn, Swernert and Dyer, and Cassels. And this is Oppenheim. It's actually fun to look at his Wikipedia entry, I think it was. That's why I get all this information these days. He actually was an interesting character. He was vice chancellor of the National University of Singapore at some point. So, and he conjectured his Oppenheim conjecture. When was this? I think I've written it down somewhere, probably on the next slide. And here's Margulis. (1929) was the formulation of Oppenheim's original conjecture. And what is it? So this Oppenheim conjecture is about the distribution of values of quadratic forms evaluated at integer lattice points. Okay, so you take your quadratic form, Q, and I've written down here what it means to be indefinite. I'm not going to go through this. It's just for the benefit of people who don't have those definitions handy. So Q is an indefinite form of signature PQ. And we're evaluating this form at the integer lattice points. And the Oppenheim conjecture says that if the form is irrational and indefinite, and the number of variables is at least 3, then the infimum over all values is actually 0. Okay, so there is no gap. Obviously, if you plug a 0 in here, it's a quadratic form, you'll get 0. So you need to exclude this point, otherwise everything will be trivial. Now, in fact, Oppenheim was more cautious. He only stated his conjecture for n greater or equal to 5, not 3. And this was because I guess he started off with a famous observation by Meyer, who observed that if you look at a rational form, now rational means the coefficients of your form are all rational.
So is it equivalent to assuming they're integers? I mean,
Yeah, it's equivalent to that, exactly, yeah.
so
You
5
just
variables
multiply.
have to have a 0, right?
Yeah, so in 5 variables you have to have, you find a non-trivial representation of 0. So if this will be a rational form in more than 5 variables, you'll always find a 0
For the min.
for the min. Yeah, exactly. So that's where he started off with, and he said, well, actually the same should be true for irrational forms. Of course, it won't be the min, it will be the inf, right? So that was Oppenheim's original.
That's a natural assumption.
So it was natural. But in fact, if you're just interested in irrational forms, it's even true when you go down to up to 3 variables. And what does irrational mean?
The integral thing isn't true for 3 or 4 variables?
Yeah, no, there are counterexamples for 3 or 4. And don't ask me to write them down right now, okay? I can't remember them. But there are forms in 3 and 4 variables where 0 is the only, gives you the only value 0. And I didn't say, I should emphasize this, irrational means here being not proportional to a rational form. Okay? So obviously, if you take a rational form and you multiply it by an irrational number, that's the same as before. We don't like that, right? So it really needs to be genuinely not being proportional to a rational form. And here, this is a little exercise for all those people who get bored during my lecture. Here is an example of a form where you can show very easily that this would not be true. So the inf will not be 0, but will be a strictly positive number. You can try to work this out. Okay. Now, how do we prove such a thing? And this, actually, Margulis' proof was a big shock to number theorists, because he was only talking about 3 by 3 matrices and sort of, dynamics on them, multiplying, these diagonal matrices and so on. So people...
It took him a long time to prove this.
Oh yeah, no, he didn't do it on a weekend. No. This is very serious stuff.
Yeah.
I just think the perception that people had when they looked at it was, oh, what is this stuff about 3 by 3 matrices? Right? Okay, so in fact, the observation goes back to a paper, and it's implicit in there, by Cassels and Swernert and Dyer. And later, Raghunathan rediscovered this, not being aware that it's in this paper, and popularized it. And Raghunathan is really credited with getting the wheel in motion on this. Now, even though the Oppenheim conjecture is not true for n equal to 2, I want to explain to you, in the simple case of n equal to 2, how you can translate the problem of the distribution of these quadratic forms into a problem on homogeneous flows. Okay? So here's the idea. Number 1, let's transform our form that we start off with into such a normal form here. And
Over the reals.
everything's over the reals. Yeah, everything's over the reals. Okay? So this is now our form, but the price we pay, of course, is that we don't evaluate this form at the integers. Then it will be a rational form, but at the points of the lattice that corresponds to M. Right? So now we have to use these lattice points in our form. Observation number 2, this form Q0 is invariant under diagonal subgroup. That's the orthogonal group of that particular form. And then what do we need to show? Given any epsilon, we find a t, this t here, so that the lattice, which we evaluate now, the form, contains a non-zero vector y, so that we're getting close to 0, yeah, within this bound epsilon. So this is a bit funny because, of course, phi t doesn't do anything to the form, but it does do something to our lattice, right? So we have this lattice in 2 dimensions, and what we would like to see is that our lattice gets arbitrarily close to a lattice for which Q naught is arbitrarily small. That's what it means, right? So if we could show that this orbit here gets dense in the space of lattices, we can satisfy this condition. Because if it gets dense, it will have a lattice vector which is very short, for example. We don't even need it to be short. We just need one of those components to be very small and the other not too large, right? That's already enough. And now, for generic M here,
the conclusion is we have to have dense orbits for this sort of diagonal flow.
Exactly. That's the conclusion. Okay. Now, the reason why things...
Some dense orbits.
Hmm?
Some dense orbits.
So for Q, no. So when you start with Q, you get an M. So M defines your orbit. Okay?
So that orbit has to be dense.
That orbit, that particular orbit, for Q to satisfy, for Q to have the inf which is 0.
So what do we know about M? So
Exactly.
It's arbitrary.
Exactly. M is arbitrary. And unfortunately, for n equal to 2, we know that there are some m's for which the orbit will not be dense. For instance, we have periodic orbits of this flow, right?
So I want to get the statement. What, even though it's false in 2, if blah, 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 then
Right.
what's the statement?
Now the statement...
Not to prove the statement. What's the statement?
No, the statement now is, if we go for n equal to 3, then you will have a bigger orthogonal group that leaves our form Q naught invariant.
No, what's the statement that this argument is showing?
Oh, okay. No. So what this statement is showing is that if I'm interested in a particular form Q, and I want to show what we had on the previous slide, here, if I want to show just this, not for every form, but just for this fixed form Q, what I need to show is that this orbit that I get here is dense. This orbit. Q determines M, and then I get this orbit M.
And the space of lattices under which flow, though?
Under the diagonal flow here, under this flow.
Yes, it says that
2. I'm an n equal to 2 at the moment.
I was saying that this action should be minimal because we don't know anything about M. So M for any M, the orbit should be dense.
Yeah, but you're already going too many steps further.
Both.
Yeah, I think everybody's right, but I want to know what the point of this slide is, to explain to you how we translate the statement of the inf of our quadratic form to be 0, how we translate that into a statement of the distribution of this orbit in this dynamical system.
So in one sentence, the statement is that if the orbit of M is dense, then the corresponding Q satisfies the Oppenheimer.
Exactly. That's the statement.
Yeah, but you used a letter M in there, so I want the statement without using letters, right? You have a quadratic form, then there's a particular orbit that should be dense, associated to the quadratic.
Absolutely.
What is that particular orbit?
That's this one.
No.
You get. Well, conceptually, this M is exactly the matrix that brings Q into the standard form Q naught. That's your matrix you can calculate. Okay.
Some one-parameter subgroup of the orthogonal group should have a dense orbit.
No, but
And in this case, the orthogonal subgroup is just a one-parameter group.
word statement of the thing. So in other words, you have a quadratic form. You have the space of lattices and homogeneous things. So then this property we want will be true if what?
If the one-parameter subgroup that leaves your original form Q invariant, if you like, acting on Z2 is dense.
Okay.
Is that better?
Yeah.
Yeah, okay. And now, when we are in n not 2, but 3 or 4 or higher, then you can actually prove that for any Q. Okay? And that's what Margulis proved, and that's a very hard proof.
And in the statement you said the one-parameter subgroup, but there are many one-parameter subgroups.
No. I didn't use one-parameter subgroup. That was an interpretation from the audience. No. When we are in N3 or higher, your orthogonal group will not be just a one-parameter subgroup. And so you just look at the action of that full group.
The full group.
For the full group, yeah. And then that should be dense. Of course, you can answer this question by looking at several one-parameter subgroups, right? That's fine. But it's the full group that should, the full orthogonal group should be dense.
Form, you want the action of its orthogonal group to be dense on the space of lattice.
Exactly.
Okay.
Exactly. Yeah? So this is like the first key step in that I'd all like you to appreciate. We had this problem of quadratic forms, their distribution at integers. We've translated it into a density statement of the action of a certain subgroup of SLNR on the space of lattices. And this is really the key point. And in this field, this step of finding the right translation of your original problem into a problem of the dynamics on homogeneous spaces is often the key step to find that. And then you work and you're using your ergodic theory, and sometimes these are extremely hard problems, as here, but then it's in the realm of ergodic theory, and it's of course difficult and hard, but conceptually I always think the translation is the first key step that you want to do. Now, without going into the details of the proofs, because I'll do this tomorrow and on Friday, where I go through a few examples in a little more detail, you can now ask a more general question. So what we've just seen is the statement that the infimum of the values of a quadratic form at integers is 0. But in fact, a more general statement is true, namely that the values are actually dense in R. So they're not only accumulating at 0, but they're actually accumulating at every point in R. And that's also what was a byproduct of Margulis' proof. So you just look at the values, at the closure, that's R. So then you can ask, well, can I say something more quantitative? And what does that mean? Well, let's look at all the integers in a big ball of radius t and count how many values of q are in an interval AB, let's say. And so the quantitative version of the Oppenheim conjecture states that these actually are becoming uniformly distributed in the sense that the number of such points is asymptotically the same as the measure of points in a big ball of radius t for which q of x is in the interval AB. And this is the quantitative version. And this quantitative version doesn't only use the density of the orbit under the action of this orthogonal group on the space of lattices that are described in the previous slides, but it uses an equidistribution statement of these orbits, right? A measure theoretic statement to get this. And what is remarkable is that, in fact, things go wrong here. This is more sensitive. So as long as your form is of signature PQ with P greater or equal than 3, everything's fine as before. But if you have, for instance, signature 2,2 or signature 2,1, you need extra Diophantine conditions on your form Q. And it'll lead a little too far on...
You say the problem's open for 2,1. You know you need for 2-1?
You know that you need
Something.
you need Diophantine conditions because you can produce irrational forms that are well approximable for which this diverges. But we can't prove that, say, if the form is Diophantine of a certain type, we can't prove it here.
Yeah.
We only know this for almost every form of signature 2-1. So that you can do, but not for a specific choice of a form, explicit choice of a form of under certain Diophantine condition. I'll get back to this point. The reason. Now let me go on. So the reason for how you can prove these things is a fundamental result by Marina Ratner. Margulis also had worked on this for a long time to trying to establish the equidistribution results that you need to prove theorems like the theorem on the previous slide. But Ratner completely solved the problem. And that, if you like, generalizes the very simple case that I started off the lecture with, where you look at rotations. Here you generalize our rotation to a general homogeneous space of the form that we're interested in, G mod gamma. And what does Ratner's theorem say? So if you look at an unipotent flow, and I'm not going to define what a unipotent flow is. The main idea of a unipotent flow is that all its eigenvalues, if you look at SLNR, for instance, should be equal to 1. That's an example of a unipotent flow. That will be the horocycle flow. Here, the eigenvalues of the flow are not equal to 1, and so this would be an example that's not a unipotent flow. So if you have a unipotent flow, Ratner proves that any measure that's invariant and ergodic under this flow has to be supported on a very, very nice structure, namely another homogeneous space that is embedded in G mod gamma. It could be the Haar measure on G mod gamma as well. That, of course, is an invariant measure, but there can be many other measures. And all these other measures correspond to subgroups H in G that have the property that if you intersect your origin lattice with H, you again get a lattice. And why do you want this? Because then this H mod gamma H is again a nice homogeneous space, and you can identify this with this coset. If you remember your group theory and your isomorphism theorem, then this is one of those. And so the left-hand side here will just give you the embedding of your space in the big space.
I thought she proved things like this much earlier than that date there.
No, she didn't. That was the early 90s was when she proved that particular statement.
Is the date of publication?
Yeah, okay. And it's in the Annals, so it was probably written up 5 years before. But no, it's from this time. So she was already she wasn't a postdoc anymore at that time. Okay, and the measure that we are looking for here is simply the Haar measure of H projected onto this homogeneous space. So this is a very beautiful, simple structure. Okay? That's not the case from any dynamical system. So if you have a hyperbolic dynamical system, your invariant measures can sit in principle on very, very complicated fractal sets. Ratner's theorem tells you if you have a unipotent flow, the invariant measures are all sitting on very nice, beautiful embedded submanifolds. And that's the key observation, and that's what
So for these diagonal
makes
flows, it's very false.
Exactly. For the diagonal flows, it's very false. Okay? And in fact, you can easily check that there are only countably many subgroups with this property, because you need to be able to intersect with this lattice, which is a discrete subgroup, and get another lattice in H. And that's exactly what makes everything work. So if you remember my first slide with the rotation, there we had a unique measure that corresponded to the Lebesgue measure. Here it can be a bit more complicated. The analog example would be if you look at a high-dimensional torus and you would just look at the Kronecker flow on this, the invariant measures then correspond to the rational subspaces in this torus. And this is just the generalization for arbitrary Lie groups. Okay, so now I've explained to you, or just given you, I hope, some feeling of Margulis's proof of the Oppenheim conjecture. I stated a quantitative version, said Ratner's theorem is a main ingredient there. So what I want to do now is I want to give you another collection of some other problems that have been solved, and then, yeah?
Well, just there's a little gap in my logic in my
Yeah.
head. We've got this first statement that the subgroup preserving the quadratic form should be dense.
Exactly.
But now that's a much bigger group than a
Yeah.
unipotent flow. So
Ah.
somehow
Yeah.
like you're using extra money.
I'm sorry. This is
Money.
a very important point. Yeah, this is a very important point. So the reason why you can apply Ratner now to these orthogonal groups is because they contain unipotence. So they're actually generated by unipotence. That's only true for n greater than or equal to 3. As you've seen, when n is 2, it's not a unipotent, and it's just a one-parameter subgroup.
So all we know about the action of these indefinite orthogonal groups is the fact that they have these unipotent flows, and Ratner's theorem applies.
Exactly.
Okay.
Exactly. So I'm now just going to give you a whole survey of some other problems without actually going into the details of the proofs, why it works. I just want to give you that impression of that this is really something that applies to a number of beautiful mathematical problems. And then tomorrow, I'll show you in a little more detail something about the Lorentz gas, but I'll come back to that. But that's just the motivation. So if you now feel a little, you haven't understood every little single step, that's my intention, because I couldn't possibly show you the complete derivation of all these things.
So just checking the thing, like this O21,
Yeah,
which is SL2R, has a unipotent.
exactly.
But this O11 just has the diagonal.
Exactly.
So you're out of luck.
Exactly. That's the point. That's exactly the point.
That's why the 3 comes in.
Exactly. Yeah. Well, it already comes in, and okay, signature 2-1, it already comes in. There is a unipotent there.
Right.
The reason why the quantitative version is more difficult has something to do with divergence of orbits in the cusps. So it's another phenomenon. So let me run through a few beautiful other areas where this has made some impact. The first one is quantum chaos. And so in this area, which recently has seen a lot of interest in the pure math community, started off in the 80s, the 70s and 80s, mainly in the physics world. But here you can formulate very clean mathematical problems. The first one is you look at a domain in R2, like this cardioid-shaped domain, and you look at the Laplacian with Dirichlet boundary conditions. Because it's compact, you know there'll be a discrete spectrum. So the eigenvalues will be ordered, and you'll have associated eigenfunctions. And one of the questions in this field is, can we understand how the eigenfunctions distribute as you go higher and higher in the spectrum? And numerically, you see pictures like this. So you see from time to time eigenfunctions which are extremely localized. Do you like to understand?
Well, the orange is a support.
Yeah. So the orange is like a high value. This is the L2. So this is the absolute value squared of the function. So if it's orange, it's a very high value. And blue means close to 0. So this guy here seems very uniformly distributed, sort of wiggling around, right? But if you would sort of integrate your absolute value squared over some domain, you probably get the area of that square of that region approximately. While here you wouldn't. Here you would get, if you integrate over this area, you would get something very small. These are called scars, scarred eigenfunctions. And one open conjecture is, can you prove that there is a subsequence of eigenfunctions which converges in measure to something singular? Oh, sorry. Okay, that's one question. And the other question is, can you show that eigenfunctions sort of become uniformly distributed? I'll get back to this. I'm jumping ahead here. Another very beautiful question is, if you look at the statistics of those eigenvalues, say you look at the distribution of gaps, that's the gap distribution. Now here you're counting how many consecutive eigenvalues are there with a gap that falls into this interval? How many are that fall into this interval? What people have observed numerically in the physics literature is that they follow a distribution that's given by random matrix theory. In random matrix theory, you take an n by n matrix, say real symmetric, to have the same symmetry as the Laplacian here. So n by n matrix, real symmetric, and then you'll take the coefficients in your matrix to be independent random variables that are Gaussian distributed with a fixed variance. And of course, you have to have the symmetry. You can only take the upper tridiagonal, and then not tridiagonal, upper, you know what I mean. You can only do these, and then you reflect over, right? Because you want the matrix to be symmetric. You get your eigenvalues. You take n very large. You can calculate analytically what these limit distributions is, and here are the curves. There are several ensembles, the Gaussian unitary and the Gaussian orthogonal here. That's the one I've just explained to you. And you see a fantastic fit. No one knows how to prove this rigorously. And anybody is interested in this, I can give you some more details afterwards, what the current heuristic state of affairs is, which is actually beautiful, beautiful stuff, even though you can't prove anything.
So one thing was the spacing between the eigenvalues of a random matrix, and the other one was the spacing of what? The
eigenvalues of the Laplacian.
Laplacian.
So that was the data that I had, right? And that was just a numerical calculation. You calculate these eigenvalues numerically.
The domain was started.
Absolutely, yeah, absolutely. It was for that specific domain. Here, if you take the circle as your domain, you can work out what the eigenfunctions are. Just the disk, yeah. Sorry, just the disk. Right? You can calculate what the eigenvalues are. You do the same statistics, and they follow an exponential distribution. The exponential distribution is exactly the gap statistics of independent random variables, or more precisely, you take a Poisson process, and the waiting times, as you know, are exponentially distributed. That's also open for the circle. No one knows how to prove this. Here is the problem of the eigenfunctions that I alluded to earlier. But let's talk about something a little more interesting or more doable from the mathematical point of view. Let's not look at these domains. They have so many singularities. Let's look at a nice hyperbolic surface. So by this I mean some compact surface of constant negative curvature. Again, you have your Laplacian, your Laplace-Beltrami operator on the surface. The spectrum is discrete. You can do all the same things. And you can ask, well, these are L2 functions, my eigenfunctions. So I can normalize them to have L2 norm 1. This means this will become a probability measure. It will be a sequence of probability measures. And you can ask, what are the possible limit points of that sequence of probability measures? Okay. And the famous conjecture is that for the hyperbolic surfaces, there's only one. Again, like measure rigidity. Okay? There's only one limit point. All the eigenfunctions become uniformly distributed. So this means you will not see subsequents that localize on anything, as I showed you in this cardioid shape picture. In fact, you can show that almost all eigenfunctions becoming uniformly distributed in the sense of density 1 subsequence. It's a famous old theorem by Schnirlemann, Zeldich, Colin de Verdier. But what about density 0 subsequences? That's exactly what this conjecture is about, that actually everything should converge to the uniform measure. And Lindenstrauss proved this in his celebrated work. In the case when your arithmetic your hyperbolic surface has additional constraints, it has to be arithmetic. And that means if it's arithmetic, you have more invariances that you can play with, so-called invariants under Hecke correspondences. The group is an arithmetic group that defines the surface, this group gamma. And in fact, it has to be of congruence type. So it's not understood yet what happens for non-congruence type groups. And he used measure rigidity. There's also some beautiful work by Anantaraman who made some progress on the question of whether there can be scars in the non-arithmetic case. But I don't have enough time to talk about these things. Right. So, about the question of eigenvalue statistics, in this case, let's look at a flat torus. What's a flat torus? You just take RD and then modulo some letters L. So here you have your eigenvalue equation, the eigenfunction are exponentials, all very simple. But now we're interested in the eigenvalues, it turns out, because these are the eigenfunctions. The eigenvalues are just the values of a positive definite form at integers, right? And the quantum chaos conjecture would be that these should behave like independent random variables. So can we prove that? Well, first of all, you need to rescale your sequence, because if you want to compare it with a Poisson process of constant intensity, you want to make sure that your values grow linearly. And so you just need to rescale this. You know how to count the number of lattice points in a big circle, or in this case, in a big ellipsoid. It's asymptotic to the volume of that ellipsoid, and so rescaling is simply given by that rule. So you take your values and you just raise them to the power d over 2. These are your new values, and if you do that and you check that they actually now grow linearly, and then you do some simulation, some statistics, and you see they actually look like an exponential distribution. We have no idea how to prove this. Okay, seems such a simple problem. Gaps between values of a positive definite form. Has to be irrational, I have to say this. If it's rational, the whole thing breaks down. You actually understand very well what's happening. A simpler question is, let's not look at the gaps, let's just look at the spacing between all pairs. That's the so-called two-point statistics. And if you think a little bit about what that is, remember, these are the values of a positive definite form. If you look at these differences, it's actually going to be an indefinite form. So we can apply the techniques of the quantitative Oppenheim conjecture. And that's where Eskin, Margulis, and Moses got interested into this problem when Sarnak told them about this. So they realized that in dimension 2, two-dimensional tori, it corresponds exactly to the case that they were just able to do under Diophantine conditions. And I worked on the same question, but I didn't look at generic forms. I took just the standard form, very rational, and then evaluate them at shifted lattice points. And there you can also show that the two-point correlation function is that of a Poisson process, in fact, in any dimensions. Margulis and Moses and Eskin could only do the two-dimensional case. And this is still an open question. So again, here, measure rigidity has had an impact to this problem. And I guess my time is over, right? We started a little later? OK. So here, this is, I think, beautiful. And that's the last chapter. I won't go into many details. But I think you'll really enjoy this. So now we're interested in a very, so already the sequences that I just talked about are a little complicated, right? You have this lattice, you have a quadratic form. It looks already a bit messy. In distribution mode 1, there are very simple sequences that actually also show this randomness. So let me explain this. So here, all I'm saying is we take a triangular array of numbers. So we're interested in each row, and the rows become longer and longer. And these are the things that we're interested in. So these are numbers in the unit interval. And here, again, you can ask, well, how random are they? First question, are they uniformly distributed mod 1? This would be this statement. Just count how many fall into a certain subinterval of the unit interval. If that's the case, that's good. Then we can ask a question about the gaps. Yeah. So the way I write it this way, just to indicate that each row can be a new thing. Not necessarily these guys have to be the same, OK?
And the X and J's are just in some row? Yeah. I mean, the zeta J's?
Yeah.
No,
so here I'm just dropping this index. I'm just saying,
fine.
I'm just dropping it because the notation would get messy. I just want to highlight that each row will depend on n would be something new that comes up. Of course, there has to be some algorithm that generates the sequence. Okay, so assume it's uniformly distributed, which is this statement. Let's look at the statistics of the gaps. Now, the average gap size will be 1 over n, so we have to count in small intervals, right, of size 1 over n. And then the question is, well, will this be the same as uniformly distributed independent random variables in 0, 1, for which the exponential distribution will be the answer? Of course, we can't do that in many problems. Easier, again, to look at pair correlation, so the distances between all gaps. And here, again, we count in small intervals, and we divide by n. We don't divide by n squared, okay? That's the question you people ask me. Why don't you divide by n squared? You've got n squared terms here. Why don't you divide by n squared? Well, because this is a very subtle counting problem. You're counting something in a very narrow region, right? So just fix one of the xi i's. How many xi j will be in a neighborhood of this? Only a finite number. That's why I only divide by n and not by n squared. Right, so here are the sequences that I love. Very simple. Fractional parts of 2 to the j alpha. There you can show its Poisson for almost all alpha. In fact, we only know it's uniformly distributed for almost all alpha. That's the famous problem of normal numbers. We can't take alpha to be pi. We don't know if this thing will be uniformly distributed. Right? Because why is it related to normal numbers? Base 2 in this case. Because the orbit 2 to the j alpha exactly produces the binary expansion of pi. If you choose the right test intervals in your, I think, just half, 0, 1, half, or something like that.
N in that first discussion.
Here?
Yeah.
Okay, you take j from 1 to capital N.
Oh.
And that gives you your nth row, right? And that's why I wanted it, because then when you go to the next row, the thing will be sort of messed up. And I also insist that they are ordered, because I want to measure the actual gaps between the consecutive gaps. There we understand it, but only for almost every alpha. Here, j squared alpha and higher polynomials, we understand that the Poisson distribution arises for the 2-point statistics. That's what Rudnick and Sarnak proved. We can't prove it for alpha equal to square root 2, for instance. It's a big problem. We don't have an analogous translation where we can apply Ratner. That's what I would love to find. I would like to say if alpha is square root 2, we also get pair correlation function that's Poisson, not just for almost every alpha.
Square root of 2?
Yeah, for square root of 2. I'll take alpha square root 2. It looks perfectly Poisson in the numerics. We can't prove anything. It's a great problem. Heath Brown got excited in this, and he couldn't do it. He could only give some sort of algorithmic characterization for those alpha that work. There are some results on the gap distribution. Let me glance over this. I can give you those slides, and you can get the references and learn a little more about this, because I want to conclude with a very beautiful sequence. And this is small powers. And so you just take n to the beta strictly between 0 and 1. And it looks beautifully Poisson. Here beta is 1/3. That's the gap distribution. You can't see the exponential curve. It's sort of behind that. But for beta equal to 1/2, something funny happens. The gap distribution actually is no longer exponential. It's the only value I know. I might be wrong. This might not be exponential. It might just look like it. I don't know. But it does look pretty close to an exponential. Now here it's obviously different. And Elkes and McMullen, in a very beautiful paper, showed that first of all, that the limiting distribution exists and is given by a certain random variable on the space of lattices, okay? And what do they use? Ratner's theorem. The translation here again of this problem into the language of homogeneous flow is the key step in this paper. And then you apply the standard techniques.
It looks a little like a random matrix distribution.
If you like, yeah, but it's actually constant here.
Yeah. Oh.
And then here it has an algebraic tail. So I think it goes down like x to the minus 2. Now, for the percolation function, interestingly, the same problem is Poisson. So that's a bit funny, but one can understand this completely. That's a little remark we made recently.
So what is special about 1/2?
What's special about 1/2 is that you can identify a certain homogeneous flow that produces these values. And is there something special about 1/3? Maybe. Maybe there is a homogeneous flow that does it, in which case I would bet it's not an exponential distribution, you see. But no one knows how to do this. In fact, there is a heuristic argument which makes it sort of clear that it should be random. But it's not clear. If you're interested, look at the Elkes-McMahon paper and try to do it for x to the 1/3 or n to the 1/3. But that's why it's special. And it'll take you, I can explain this to you if you want an extra session. I can explain this to you, how this problem is translated. And here is another thing, and this is going to be my final slide. If you have a student project, this is a great project. Just look at the question of log n, fractional parts of log n. There you can do everything explicitly. And if the base of your logarithm is very close to 1, you'll get something that looks almost like an exponential. Important that the base is transcendental in this. So that's a short note by Andreas Strömbergsson and myself in the bulletin of the LMS. So tomorrow I'm going to talk about this Lorentz gas, very old problem in statistical mechanics, where you're interested in a particle cloud that moves in a certain scatterer configuration, and where people expect, in the limit of a low scatterer density, to find a classical linear transport equation, the so-called linear Boltzmann equation. And what we show is that when your scatterers are on a perfect lattice, like in a crystal, at 0 temperature probably, 0 Kelvin.
So the blue dots are fixed.
Fixed, yeah, fixed. And you look at a
pinball machine.
yeah, exactly. And you look at these particles that fly around here, and you want to understand what is their dynamics when the radius of these things is smaller and smaller. And what we show using techniques from measure rigidity is, I'm not going to go through this, don't worry, I'll do that tomorrow, is that when you have a periodic setting, you actually get a new transport equation that even the physicists didn't know about, and that's what I'm particularly proud about. And so this is probably my own most important contribution to this area of statistical mechanics, and the key was really to use the techniques from measure rigidity, which in this area no one had used before, to solve this long-standing problem. And then on Friday, if you still have the energy, I'll tell you a little bit about networks and graphs and how we can use measure rigidity techniques there to solve some problems. Okay? I'm really sorry I went over time a little bit, but I hope you enjoyed it. Okay.
So, but for beta not equal to 1/2, it is still anticipated that there is some translation to the homogeneous?
No.
Because
You could think, okay? So you could think maybe you should go, so the Lie group that, or the homogeneous space where everything works, is SL2R semi-direct product R2. So you could, for n to the 1/2. So when you go to n to the 1 cubed, you should maybe expect to go to a higher rank group, but I don't think so. Okay, yeah, people should go, and then we can discuss.